Okay, so in the last part of the lecture, what I'd like to do is try to analyze this algorithm and show that it has low regret for any adversarially chosen sequence of cost vectors. Okay, so here's our result for all adversaries. Assuming the costs are chosen between 0 and 1, multiplicative weights run with parameter eta has expected regret at most 2 square root of 1 of k over t, where when we select eta to be exactly ln of k over t. So let's prove that. All right, so what's the idea of the proof? The idea is that we're going to look, we're going to track zt, the sum of weights, sum of the weights, and we're going to have like two basic facts. I'm going to sort of two sublemmas. Okay, two parts to the proof. So the first is that the first thing is going to be that whenever D has high expected cost, then ZT will decrease in that time step. It'll decrease a lot. Okay. So specifically, we can let V sub t be the expected cost at time t. So that's this inner product. So this is expected cost at time t conditioned on whatever happened before. And now what we're going to show is that zt plus 1 is always at most zt times e to the minus eta. Sorry, try that again. E to the minus eta times v sub t. Okay, times this expected cost. So one consequence of that, so this we will prove. Okay. A consequence of that is that after all is said and done, the final z, the final like sum of the weights, will not be very big. So it'll be like z1 at most, or rather at most z1 times the product of these factors that have accumulated over all the time steps. Okay, so at each time step, we're losing e to the minus eta times v sub t. And so after t time steps, we lose e to the minus eta times the sum of all the costs experienced, the sum of the expected costs along the whole trajectory, the entire sequence, okay, from t equals 1 to t of v sub t. And indeed, this is the thing we want to, bound. We want an upper bound on this. Okay. Because the sum of the VTs, that's the sum of the expected costs over all around. So that is in particular the expected cost over the expectation of the sum of the VTs is the total expected cost for the algorithm. in that with that adversary. Okay, and Z1, so this is just K, right? Because it starts off with, all the weights start off at 1, so the initial sum of weights is K, and then it drops over the course of the algorithm. And the more that the more that D pays in expected cost, the more this Z drops. And so what we're going to show is that, well, this is going to be what's called a potential argument. We're going to show that the Z quantity can't drop too far. All right, so the second step is to show that it can't drop too far, and that we show this way. We say ZT is at least 1 minus eta times the cost of the best action in hindsight. 1 minus eta times opt, where opt is the minimum over A of the cost of the best action in hindsight, which equals 1 to T. Okay, and here I'm not opt is not the best average cost; it's the best total cost, and we'll have to divide by T to get everything to work out the way we want. Okay, so we'll prove 1 and 2, and in fact, we'll for 2 we're going to prove something. We're going to strengthen it just a touch. So what we actually need to show is that this is at least. This thing, we need to put it in the form e to the something so that we can compare kind of apples to apples when we put together 1 and 2. All right, so let's show 1 and then we'll show 2. So proof of 1. Okay. So let's look at ZT plus 1. All right, so what we need to show is that it's at most ZT times some factor that depends on the expected cost at time T. All right, well, this is just the sum over actions of the weights of the actions at time T. And that's, by definition, the sum over the actions of the weight at time T times 1 minus eta times the cost. The appropriate entry of the appropriate cost vector at that time. All right, so the first thing we're going to do is we're going to sort of try to put this in some form. The problem is adding up exponentials is a pain. And so we need to put this in some form where where we can like add across actions. And the fact we're going to use is that for all eta less than a half, less than or equal to a half, or between 0 and a half, for all eta between 0 and a half, and for all x between 0 and 1, 1 minus eta to the x is less than or equal to 1 minus eta x. So that's just like a little fact from calculus that you can check by plotting or prove using Taylor expansion. But why so the intuitively what's going on is when eta is very small, like 1 minus eta to the c is really equal to 1, like 1 minus eta to the x is really equal to 1 minus eta x. Or very close to it anyway. Okay, and that's because when eta is small, 1 minus eta to the x is very similar to 1 minus eta is basically e to the minus eta. All right, so just plugging that in, we get the sum over A of the weight at time t times 1 minus eta CTA. And now we can sort of add up, now we can add things up. So what is this? This is the weights add, so we get ZT, the previous ZT, times 1 minus, and then what do we get in, if we pull ZT out front, what we get is a sum over A's of the weight, so that's 1. And then minus the sum over A's of PT sub A, C sub A. So this is our expected cost that we want. So what we get is ZT times 1 minus VT, what we call VT. Times eta, sorry. Okay, and now, now we can just use the fact that we can put this back on an exponential scale. So this is at most e to the minus eta VT, and that's just since 1 minus x is a lower bound for e to the minus x everywhere. Okay, so what we've done here is we've sort of, by putting everything on, we managed to take this sum and get it into a form where we could add across the entries, across actions. And that allowed us to get this like clean multiplicative bound on how much progress, how much ZT is shrinking. Okay, so we're done with claim 1. And now we have to prove claim 2. So claim 2 was that ZT plus 1 is big. It can't be too small when there's a good action in hindsight. Okay, and indeed, one thing we know is that ZT plus 1 is the sum of all the weights at time t plus 1. In particular, it is the weight at time t plus 1 of A star, which is the best action in hindsight. The best thing in hindsight. And so this is just the sum, sorry, it's 1 minus eta times 1 minus eta times the total cost of A star, the cost over the entire execution of A star. And then we're just going to bound that in terms of something that's like easier to compare to the thing that came out of step 1. So this is eta squared times the cost over all time of A star. Okay, and this, again, this is just some simple inequality about exponentials, since, sorry, this should be greater or equal to. So 1 minus eta is at least e to the minus eta squared for eta less than a half. Okay. All right. So let's put these together. So on one hand, we know that, e to the minus eta squared times the cost so far, the cost of A star. Let's write it like that. That's at least, ZT plus 1 is at least that. And on the other hand, we know it is at most e to the minus eta times the sum of the VTs, the expected costs actually experienced by the learner, by D. And so we can, taking logs and adding a minus sign to get things like positive, we get that eta plus eta star times the cost of the best action in hindsight is at least eta times the sum of the expected costs experienced by the learner. And now we notice that this thing here, this is at most t, right? So what we're going to do is we're just going to rearrange our terms a little bit. Oh, sorry, we lost the factor of d. So there was a d here, and then it winds up over here when we take logs. Sorry about that. Okay. Okay, so let's just, this means that eta, we want, the thing we're trying to bound is this quantity, right? So what we get is the sum over t of these VTs. If we divide through by eta and move things over to the correct side of the equation, what we get is, sorry, let's compare it to the cost overall, the entire sequence of this best action. So that what's left over here is eta squared times, here, I'll just write out the extra step. T plus log of d over eta. Sorry, this is, there we go. Okay, and so dividing through by t to get an average regret bound, we get, so 1 over t times the sum of the VT minus the average cost for A. I'll write out what that is. So A star time t. Okay. That's at most eta times, we'll use the fact that this thing is at most t to get eta times 1, plus log of d over eta times t. And if we set eta to be just the thing we need, so ln of k to, we set eta to equalize these two terms. Okay. What we get is at most 2 times the square root of log of d over t. Okay, so we're essentially done with our proof, just to make sure that the pieces all make sense. So that my expected regret, that's equal to the sum, whoops. So it's equal to the sum over time steps of the expected cost at time t minus the expectation of the cost of the best action in hindsight, best hindsight action. Okay, so it's a little, just to make sure we're paying attention to the expectations properly, this expectation is over any random choices made by D and the adversary, and same thing in the other case. So this is the coins of D and the adversary. And so what this is this is at most the expectation of the sum over t of the VTs. So the VTs are actually random quantities that depend on the execution, but they are themselves expectations of cost condition on, so let me just write it this way. This is the expectation of the cost at time t conditioned on the choices that were made at previous times. Okay, minus the cost of the best in hindsight. And so what we actually get is we get like the expectation of this sum over the execution of Vt minus, so this is all t times the regret because we want to average later. Okay, and so, you know, Vt is a random quantity, A star is a random quantity that depends on the particular execution, but by linearity of expectation, it works out. And the sort of cool thing is like, this is actually bounded with probability 1. And so that means the expectation in particular is at most 2 square root. Like it's bounded. What we showed is that the thing inside the expectation is bounded with probability 1 by square root of log d over t. And so we're done. Okay, so what have we shown? Going back up to the top, we've shown the following theorem, you know, that here's this algorithm, the multiplicative weights algorithm, and it has the property that for any adversary, in retrospect, the sum of expected costs it paid, or the expectation of its regret relative to the best action in hindsight, averaged over time steps, that'll go to 0 as time progresses. So it will very quickly effectively converge to the cost of, or to something that is at most the cost of the best action in hindsight. Could be lower. And it turns out that's the fact, there are some very special things about it. So the dependency of the regret is only logarithmic in the number of actions. And to get that kind of dependency, you need to penalize actions kind of exponentially quickly as their costs increase. On the other hand, it also has this like 1 over square root of t dependency. And it turns out you can't really do any better than that. We'll see that even if the adversary is just making totally uniform random choices, we will get every algorithm will experience regret on the order of square root of log k over t. So this is really actually optimal for the setup we're in. Okay, and in class, we'll take some time to explore some questions that help us wrap our heads around this algorithm and its properties.